Hi, so today we will be deriving the Navier-Stokes equations. In particular, I'll be focusing on deriving the continuity equation, also known as the mass transport equation. And before we dive in, I would like to note that the Navier-Stokes equations are a set of equations that describes a fluid flow across space and time. So starting off with the continuity equation, this equation describes how mass flows through space. So here, let's create our control volume. Make it nice and big. And we'll have our directions. We'll say that this is our x direction, this is our y direction, and this is our z direction. And the size of our control volume is has the sizes of dx, dy, and dz. And this is saying that we are at the size is of our control volume is infinitesimal, which means that it's the smallest size that you can possibly imagine. So the continuity equation or the mass transport equation states that the sum of the mass flow rate going in the control volume minus the sum of the mass flow rate going out of the control volume equals out to be the change in mass with respect to time, dm dt, dm over dt. So since we're in 3 dimensions, this will have 3 components. So let's focus on the x direction first. We have the mass flow rate in the x direction at x and out here. We have the mass flow rate in the x direction at x plus dx. Similarly, for y, m dot y at y, we have m in the y direction, m dot y, in the at y plus dy. And lastly, we have our mass flow rate in the z direction. M dot z at z and m dot z at z plus dz. So before we move on, let's define some terms. M dot is the mass flow rate, which equals out to be rho, which is the density of the fluid, times A, which is the cross-sectional area that the flow travels through, and the vector V, which is the vector components in 3 dimensions. So v vector equals out to be, it's the velocity. So it's a velocity in the u, in the u, v, and w. So u is the velocity in the x direction, v is the velocity in the y direction, and w is the velocity in the z direction. And I would also like to note that the volume of the control volume equals out to be dx times dy times dz. So these are just important notes to reference to when deriving our continuity equation. So the mass flow rate at the inlet is the following. Let's say x, for example, the x direction at x equals out to be rho times u, because since we're in the x direction, we are using u, the u velocity, times a. And the area that this mass flow rate travels through is dy times dz. So our area is dy times dz. And our mass flow rate going out is a little bit different. It's m dot x, the mass flow rate in the x direction at x plus dx will equal out to be the mass flow rate at x dz plus the mass flow rate at dx. So partial x rho u dy dz dx. Similarly, in the y and z direction, we have the following. Partial y rho v dx dz times dy. And lastly, we have m dot z at z equals rho w dx dy m dot z z plus dz equals out to be rho w dx dy plus partial z rho w dx dy times dz. So the sum of our mass flow rate at the inlet will equal out to be rho u dy dz plus rho v dx dz plus rho w dx dy And our mass flow rate, the sum of our mass flow rates going out of our control volume is rho u dy dz plus rho v dx dz plus rho w dx dy plus partial x rho u dy dz times dx plus partial y rho v dx dz dy plus partial z rho w dx dy times dz. And when we subtract m dot in minus m dot out, we get the following. These terms cancel out. And these terms, since it's minus m dot out, these terms go negative. So we get negative partial x rho u plus partial y rho v plus partial z rho w. And here we have dx, dy, dz. Since all these terms have dx, dy, dz, we are able to pull it out. And recall that dx, dy, dz equals the infinitesimal volume in the control volume. So this will, in fact, equal out to be the same thing. Partial x rho u plus partial y rho v plus partial w rho z dv. So let's take a look at the term dm over dt now. Since density is mass over volume, we can say that partial rho, partial t, dv equals out to be that dm dt equals partial rho, partial t times the infinitesimal volume. This will be equal out to be this term, partial rho u, partial x plus partial rho v, partial y plus partial rho w, partial z dv. And here we can cancel out dv terms on both sides. And that will leave us with, if we take this term and bring it over to the left-hand side of the equation, we get the following. Partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w over partial z, which equals out to be 0. So this is our mass continuity equation. This is our continuity equation that we have derived. And its vector form will be the following: partial rho partial t plus the gradient dotted with rho v vector. And give you a little context, the gradient vector is equal to a partial derivative of any quantity, partial x plus partial any quantity, partial y plus partial z. And we are dotting this gradient with u, v, and w. So that's what we get here. And lastly, if we have an incompressible flow, for incompressible flow, rho, which is the fluid density, does not change. So partial rho partial t equals to 0. And plus, we can pull all of these terms, in all these terms, we can pull rho out. So therefore, for an incompressible flow, our continuity equation is the following: partial u partial x plus partial v partial y plus partial w partial z equals 0. We'll say that, star this and say that this is the continuity equation for incompressible flows or incompressible flow. And we'll say that this is the vector form. And there we have it. This is the derivation for the mass transport equation, or the continuity equation. So the notes for this video will be available to you for free. There will be a link to the notes down below. If you have any questions about the derivation process for the continuity equation, please ask down in the comment section. And I plan on having the Navier-Stokes momentum equations derived and have that uploaded to you as soon as possible. Thank you so much for your attention, and have a great rest of your day.